Embedded Vision Alliance and Khronos very much, I think, share the same vision for making computer vision and machine learning software development, efficient software development on specialized processors that are cost efficient and energy efficient, making that accessible to hundreds of thousands of developers who don't have and probably don't want detailed knowledge of the architectures and the software tools and so on. Khronos has been really active in the last few years, developing a number of standards, some of which are already deployed, some of which will, as you'll hear from Neil, soon to be deployed, others of which are in the kind of formative stages. And so I'm really pleased that Neil Trevitt, who's president of Khronos, has come to share an update on the Khronos software standards, current and future, related to computer vision and AI. Neil, thanks very much for being here.
Great. Thank you, Jeff. It's an honor to be here. I have a gravelly voice I'm recovering from a cold, so I might need to use this. If I need to repeat anything, just shout. So, as Jeff says, we're going to be giving you, in the next 30 minutes, an update on vision standards that are being developed at Khronos for embedded vision and inferencing. If you haven't come across Khronos before, we're an open standards consortium, about 140 companies right now, everyone from Google and Apple all the way down to small one-person startup companies. We really welcome participation because this is the place, Khronos is the place where the industry can come to work together with 140 of your closest competitors to create open standards that are good for your company and good for the industry. So we tend to focus on, every standards organization has an area of focus. Khronos' area of focus is connecting the software to silicon. So we have a bunch of IHVs creating awesome silicon processors. We need to enable the developer community to reach into that acceleration to deliver awesome end user experiences. So we have about 15 active standards right now. We have some of the 3D ones, Vulkan and OpenGL. We have AR and VR ones. That's the new standards, not released yet, OpenXR. We have some 3D file formats. But what we're going to be talking about today is the set of standards that are related to vision and inferencing acceleration. And there's a little handful of them there. And it can be a little complex how they kind of interact and when would you use one over the other. So I'm going to try and give some clarity. A lot of the vision processing use cases now being served by inferencing and machine learning. So we've tried to take a step back and show how, if you want to use standards for vision and machine learning, what standards would you use and where within the training and inferencing process. So if you're using neural networks, the first stage is to train your neural networks. That's typically done on desktop or cloud hardware. We have a number of APIs that you may use if you want to use open standards. There's OpenCL, which is general purpose heterogeneous parallel programming. SYCL is a layer on top of OpenCL to let you get to that heterogeneous programming using standard C++. And then we have Vulkan, which is primarily known as a 3D rendering API, but actually it's, as we'll explain, it's transforming into a GPU API. So if you have systems, either mobile phones or desktop or cloud-based systems that have GPUs, then Vulkan is going to be providing more compute, and compute that's relevant to inferencing and vision processing as well as the 3D rendering. So we'll talk about that. Once you've trained your network, you need to get the trained network over to your edge system, your embedded system. And we have a file format that's just about to launch called NNEF, Neural Network Exchange Format. And then you want to execute your neural network. And the primary vision API we have at Khronos is OpenVX. VX stands for Vision Acceleration. And we'll explain in a moment, VX has just shipped a neural network extension that lets you not just do traditional vision processing, but now also neural net inferencing. Some of the neural net runtime frameworks, as well as the training frameworks, are coded in C++. SYCL, which is that layer on top of OpenCL, might be useful for some folks there. And then if you want to use open standards to implement your OpenVX on your hardware, there's a couple of choices there too. OpenCL, primarily for DSP and embedded processors, and if you have a GPU, increasingly Vulkan. So that's the big picture. Let's kind of dive into each of those. Let's start with kind of the heartland of what Khronos is doing for vision processing, OpenVX and NNEF. So NNEF is solving a classic fragmentation problem that's rapidly occurring right now in the machine learning industry. We have a number of authoring frameworks. They're rapidly evolving. There are dozens of them, and there are going to be dozens more very soon, probably. And a whole bunch of inference engines, anything from DSPs to dedicated hardware, tensor processor units, GPUs, FPGAs. There's probably hundreds of those being developed and deployed as we speak. So we have dozens of training frameworks needing to export their trained neural networks to hundreds of inferencing engines. This is a real classic fragmentation. A lot of industry friction to get your trained network from your training tool of choice into your inferencing engine of choice. And so NNEF is intended to help with that fragmentation problem. It's a general purpose file format that doesn't dictate any runtime behavior. It simply encapsulates the topology and the weights of a trained neural network. Any tool would be welcome and able to export to NNEF, and any inferencing engine would be able to import. So NNEF 1.0 is coming up to its provisional release. We're actually aiming to get this out before the end of the year, so it's literally the next week or two. So watch the skies for an announcement from Khronos on that. So the first focus of NNEF 1.0 is going to be on getting trained networks into the inferencing engines. On the roadmap, we might do more around circulating a network around the training loop, but 1.0, we're really trying to get the inferencing engines enabled. Of course, neural networks is a really active area of research. So NNEF 1.0, we've taken care to cover all of the well-proven network topologies, but we realize we're going to need to work pretty hard to keep up with new network topologies as they become adopted through the industry. When we do launch NNEF 1.0, there's going to be some supportive open source projects. We have a baseline importer and a baseline exporter, and they'll both be in open source. So if you're looking to export or import, you'll have a starting position. You won't have to do everything from scratch. And we will be also putting an open source validator into GitHub. So you're generating or using an NNEF file, you'll be able to check whether it's well formed. So NNEF works very closely now with OpenVX. So I think we've talked about OpenVX a few times, but just to remind folks, OpenVX originally came from accelerating traditional vision processing. And a GPU API like OpenGL or Vulkan has it easy in some ways because you know you're going to be executing on a GPU. There's no real other viable commercial architecture. But for vision processing, of course, that's not true. You can be running anything from a multi-core CPU, GPUs, DSPs, FPGAs, dedicated hardware, ISPs. So how can you create a programming API that gives you portability across that diversity of hardware architectures and still enable good performance? Well, the answer is to go up in terms of abstraction And OpenVX doesn't give you the level of control of OpenCL or Vulkan, but it gives you something perhaps even better. It's a high-level abstraction that's a graph, and you can express your complete vision processing pipeline in this directed graph, and then you can optimize and map that graph to your hardware before any cycle starts to execute. So there's a couple of advantages, as well as the portability, because you're not programming to any specifics of the underlying hardware. It's easy for the developers because they're basically clipping Lego blocks together. They don't have to understand the underlying hardware. And although it's a big responsibility for the hardware vendors to take that graph and map it onto the silicon, and that can be a non-trivial process, but it is an opportunity to add value. And the good news is unlike function call-based APIs like OpenCV, you do have everything you need to do global optimizations on the entire graph before you execute the graph at all. So how do you use OpenVX? Well, you basically connect the dots. I mean, this is an example graph down here, and these are the API calls. You're basically connecting the lines together between the various nodes. In terms of evolution, OpenVX 1.0 started shipping in 2014, so we're 2 or 3 years in. There's a bunch of people that are shipping 1.0. These are the silicon vendors. OpenVX 1.1 shipped in May 2016, and so a bunch of people now beginning to move their implementations over to 1.1. 1.1 primarily gave us a lot more Lego blocks, a lot more nodes that you can use to construct your graph. There are some pretty awesome open source tools out there, AMD, for example. They actually announced them here at the Embedded Vision Summit about a year ago, I think. But they do graph optimizations, rapid scripting, and prototyping. If you're interested in VX, that would be an awesome place to start. That runs on your desktop if you want to try things out. OpenVX 1.2 is the latest release, and that is relatively new. The spec shipped in May, and just a couple of weeks ago, we shipped the adopters program. The adopters program gives you all of the conformance tests and the process by which you can become officially 1.2 conformant. So that's only been a few weeks, but I would start expecting the silicon vendors to keep shifting right as now we have the adopters program for 1.2. Significant new functionality in 1.2, things like conditional node execution, so a lot more flexibility. The results in the intermediate nodes can dictate how data flows through the graph. A lot more Lego blocks again, and some really key extensions. The really important one is the neural net extension, but we can also save and restore the graph, 16-bit operations, and last but not least, safety critical. So we'll talk about that in a moment. A lot of the Khronos APIs are beginning to get safety critical versions. The kind of things we're talking about on the roadmap, probably, again, the most important one is NNEF import. OpenVX and NNEF working increasingly close together. As soon as NNEF ships, we'll be working to have an extension to enable import into an OpenVX graph. So these are some of the new functions. I won't read them out, but they're there for you in the PDF when you get it. As I say, conditional execution through the graph is probably one of the most important, and the neural network extension. Let me explain a little bit more about that one. So the realization, of course, is that OpenVX is a graph building API, and a neural network is just another kind of graph. And the neural net extension gives us more Lego blocks, where the Lego blocks are mapped to the different types of layers that you would have in a neural network. So we have things like convolutional layers, activation layers, pooling layers, fully connected layers, for example. And you can connect those layers together with tensor objects. tensors connecting the different layers together. So now you can, using the OpenVX Graph API, continue to have your traditional vision nodes. You might be doing your front-end sensor processing, through a traditional vision node, and then feed that into a neural net subgraph within your overall OpenVX graph. So you can mix and match the traditional and the neural net processing. Now, a traditional OpenVX graph, you have some filters and histograms. Might be a couple dozen nodes tops in a traditional vision processing algorithm. But of course, a neural network can become extremely complex, extremely fast. You probably wouldn't want to spend too long connecting all the dots for a neural net through an API. That's why it's kind of essential that we're going to be able to import a completely trained neural network graph into an OpenVX subgraph without having to go through the connect the dots API. So the two kind of complement each other really well. Of course, NNEF you don't have to use NNEF with OpenVX. The NNEF is just a standalone, self-coherent neural network description. You can import it into anything you want. But obviously, because we're building both, we're making sure that VX and NNEF work well together. The safety-critical version of OpenVX is kind of cool. There's the safety-critical versions of the kernel's APIs. We try to minimize the cost and the effort to do safety certification. And one of the big things we've done, for example, in OpenVX SC, is we use the ability to dump out the graph and then re-import it. That means the runtime deployment feature set is only for importing a pre-built graph. We can take out and not ship in the runtime system all of the development functionality that we need in OpenVX. That makes the runtime system significantly simpler and easier to safety certify. This is not the first safety-critical API we've done. The first one we did was actually in the 3D space, first for avionics displays and then automotive displays. We did a safety-certified version of OpenGL ES, which we called OpenGL SC. But there's actually a number of APIs now on the computer vision side where we need safety certification, OpenVX, and there's OpenCL, safety certifiable TSG. That's a subgroup has just been formed. And we have this thing we call the SCAP. It's an invitation for people that are really into and have experience in safety-critical systems. You don't have to be a member. We can invite you in. The SCAP is trying to figure out what are the key ways that we should be building these kinds of safety-critical APIs. Because it turns out that not a lot of people have done this before. So if you're interested in helping steer how kernels defines these safety-critical APIs, please let me know. We'd be glad to invite you in. All right, so we've covered NNEF and OpenVX. Let's talk about OpenCL and SYCL that layers on top of OpenCL. Again, we've covered OpenCL a few times, but again, to remind you, OpenCL is a very low-level, explicit way of programming any heterogeneous processing resources you may have in a system. CPUs, GPUs, DSPs, FPGAs, even dedicated hardware blocks. The way it works is that you have either C or C++ kernels, and then you have an API that lets you figure out what processors you have in a system, compile the kernels to those processors, distribute the work, and bring back the results. So you get to control everything. The latest version of OpenCL 2.2 just shipped in May, so just a few months ago. And the key thing we did with 2.2 was bring the C++ kernel language into core. So now with a 2.2 implementation, you can rely on C++ as well as C being there for coding your kernels. Quite a few companies are shipping OpenCL. It tends to come in waves. The desktop guys tend to ship first, then the mobile guys ship typically a year or two later. The FPGA guys are getting everything they need from 1.0 now. But I think the future, perhaps, is the embedded space. Marvell and TI are shipping OpenCL 1.2, and we're expecting to see more DSP implementation ship. You can use OpenCL directly, but actually a lot of people actually benefit from OpenCL through using a higher level library that uses OpenCL as the back end. And OpenCV, I'm sure it's familiar to many here. OpenCV uses OpenCL for GPU offload, Halide for image processing. And increasingly, a lot of the neural network training frameworks, TensorFlow, Caffe, they both have now OpenCL backends during the training phase. And one of these layered libraries is SYCL, which is a Khronos standard. And the idea behind SYCL is to use compiler technology and to use the language flexibility of C++, basically lambdas and templates. Using lambdas and templates, totally standard C++ syntax, you can indicate to the SYCL compiler which parts of your code are actually kernels that you want to be offloaded to your accelerator silicon. And then it all happens automatically for you. The SYCL compiler will compile the templates in the Lambda-based code, take the accelerated code off through the standard OpenCL compilers, running everything else on the host and doing all the plumbing between the two. So if you have a large amount of C++ code, and it turns out a lot of the linear algebra libraries, a lot of the vision libraries, and a lot of the machine learning training frameworks are actually coded in C++. This can actually be a really fast way of getting accelerator offload. And the compilers we're finding now are good enough that in many cases, the performance going through the SYCL compiler is actually better than hand-coded OpenCL code. So depending on your application, you can get fast deployment and good performance. And we have actual news where we've actually just shipped SYCL 1.2.1 today, 6 o'clock this morning. We wanted to announce it here at the member meeting. So it's kind of a weird, it's called 1.2.1 because it runs on top of 1.2. So 1.2.1 sounds like it's just a maintenance release. It's actually a pretty big deal. We've now have multiple implementations of SYCL 1.2, and we've put 2 years of working with the machine learning framework guys. They've actually, TensorFlow, for example, now has a SYCL accelerated backend that goes alongside the CUDA backend. All of that experience, it's taken about 2.5 years to really make SYCL production quality, and that's all been encapsulated now in SYCL 1.2.1. So if you're into C++ accelerated offload, I encourage you to take a look. Where are we going in terms of roadmap for OpenCL? There's actually three roadmap threads we have ongoing. One of them is actually being driven by SYCL. SYCL isn't the only C++ acceleration framework. CUDA, obviously, is one, but also frameworks like C++ AMP from Microsoft. They're all kind of pretty similar, and everyone working in this space actually would like standard ISO C++ to have parallel programming built in. It would be kind of cool not to have SYCL or C++ AMP, but just use standard C++. Now, the ISO guys are working on it. ISO have to move carefully. It can take quite a long time. But Khronos is taking a lot of the learning from SYCL into the ISO committees, helping this longer-term goal hopefully to come to pass. I mentioned that a lot of people want to use OpenCL for DSPs. The DSP domain, if you want to have this low-level runtime system that gives you explicit control, OpenCL is pretty much the only thing out there. But there's been this kind of disconnect, and we're going to fix it. Because OpenCL started out as primarily a desktop and supercomputer API. And so we still have that heritage built into the spec. For example, if you want to be OpenCL compliant, you have to have 32-bit IEEE floating point. And for many DSPs, of course, that's not good, because you may not need it for your use case. And that's even more, I think, the case for vision and inferencing DSPs, where we're going down to 16-bit or even less integer. So one of the things we're doing with OpenCL is we're going to be doing a DSP profile, so enabling DSP vendors to be fully conformant, but with an appropriate set of functionality, specifically targeted vision and machine inferencing use cases. And the third way that OpenCL is evolving is we're going to bring some of the advanced compute capabilities from OpenCL into Vulkan. So why would we do that? Let's talk about Vulkan. Vulkan, you might say, well, this is an embedded form. Why are we talking about a 3D rendering API? Vulkan, just like OpenGL before it, has pretty good compute. And Vulkan over time is going to get much better than OpenGL in terms of compute. The class of compute that we can use for vision processing and inferencing. And it comes down to adoption. For example, Android never adopted OpenCL into their platform, but they have adopted Vulkan into their platform. So if you're running on desktop or mobile systems and you have a Vulkan-enabled GPU, then it becomes an interesting deployment vector. You can use Vulkan for accelerating a bunch of useful stuff. And so Vulkan is pretty much everywhere. All the GPU vendors are shipping drivers. It's on desktop and embedded, even game console, mobile systems. The VR guys are into it. All the games engine guys are into it. The number one question we get on Vulkan, though, is why can't I run it on Apple? We can't ship Vulkan on Apple, not through engineering reasons, but through business reasons. Apple, through business reasons, do not enable third-party APIs. So we went and said, well, let's create a fourth API, because there's DirectX 12, and there's Metal, and there's Vulkan. They're the three new generation APIs. DirectX 12 is on Windows 10, Metal is on Apple, and Vulkan is kind of everywhere, apart from Apple. So you said, well, this means there's a real problem for the games and 3D developers, because they have to have two, possibly three backends for every application that they do. So initially we thought, let's go and make a fourth API that can be portably mapped. But the developers told us that's a horrible idea. 3 APIs is bad, 4 APIs is even worse. So we went back to the drawing board. Now we're creating a universally portable subset of Vulkan. We're doing quite deep analysis into Vulkan, DX12, and Metal, and figuring out what is the subset of Vulkan that you can map at full performance onto underlying APIs like Metal and DX12. And it turns out it's around 85% of the Vulkan API, and that's going to get bigger over time as Metal and DX12 evolve. So we're going to be shipping runtime libraries and compiler open source. You can take a Vulkan program and run it everywhere, literally everywhere. Apple, UWP, which is another lockdown platform, pretty much anywhere you have a GPU. There's some open source projects that we're using to really make sure that we get this deployed quickly. In terms of Vulkan evolution, there's a lot of compute going in. So there's already Vulkan extensions for increased shader language flexibility that includes better efficiency and performance for vision and imaging. But that's the first step, I think. There's going to be a lot of work over the next year or two in bringing even more dedicated functionality into the Vulkan API for the kinds of applications that are interesting here. Again, recognizing, of course, this is GPU focused, so for many folks it may not be relevant. But for those that do have a GPU, hopefully this is interesting. We have some interesting projects. Adobe turns out have 200,000 lines of OpenCLC. That's their production code for Adobe Photoshop. They want now to run it on Android. They don't have OpenCL on Android, so they're going to use Vulkan instead. But we've already used the enhanced Vulkan capability with a compiler. They've now been able to port all those 200,000 lines on top of a Vulkan at full level performance. So Vulkan's kind of interesting because we have the universal portability and we have soon OpenCL Class Compute. So OpenCL Class Compute everywhere is, again, relevant hopefully for some folks. So this is how it all kind of fits together. Again, OpenVX is really the core of Khronos' vision processing energy because it lets you run on any hardware architecture, because it's a high-level abstraction, which is great for programming, great for optimization. For those that want to use standards to implement perhaps their OpenVX or to enable their developers to get down to a lower level, OpenCL is kind of focusing on DSPs and embedded processors, and Vulkan for GPUs. I wanted to spend a couple minutes just trying to encourage you guys to get involved if you're not already. There are a bunch of Khronos members here in the room. But just in terms of the way we're organized, each of the API standards that we've talked about, there's a working group, and any company can join Khronos, and the working groups get to produce the spec, open source tools, conformance tests, and you join, you get access to all of these working groups. We just have introduced a new membership tier. If you're a smaller company, you may not be able to afford the 18K annual fee. So now we have 3.5K for smaller companies. It's $175 per employee, so it ramps up. If you're academic, it's 1K. So we encourage people to get involved. We're trying to reach out to the communities, even if people are not members. We're putting an increasing amount of information into open source. Increasingly, the specs are in open source. So if you find a bug in a spec, you can actually help us fix it. And all the conformance tests are increasingly in open source too. And last but not least, we have advisory panels. Even if you can't get involved with all of that, we can invite you into an advisory panel. There's no cost, and we want to get your input. And we have advisory panels for Vulkan, OpenCL, SYCL, and NEF, and hopefully OpenVX soon as well. And I'm going to finish with one question, perhaps to talk about over lunch. We still don't have an open standard for camera control. We had a project called OpenKCam a couple of years ago. We didn't get industry momentum behind it. Platforms like Android, of course, have a camera API. But as we get in multiple sensors, different types of sensors, such as depth sensors, and we want much lower granularity control, real-time control, perhaps there is a need for an embedded vision-focused camera control API. Should we reinvigorate OpenKCam? It's an interesting question. I'm sure there are many people here with a view. I'd love to talk to you about that during the day. So that's it. So hopefully that was useful. And again, Khronos, we live and die by participation. So please come and help us create these standards. Thanks.
Thank you very much, Neil.